Um, okay, so once again, the point has been up until this point was the question was setting up differential equations and how to do it. That's the main challenge. Differential equations and difference equations. So the difference equation is simply made up of, it is produced in a sequence. Okay, so sequence, and then that sequence, if that sequence is available, you can find it. And then only once we found it, we might do more and then go to differential equation after the limit. So that this is described here in this list right here. Okay, and then which brings us to that limit, brings us to the place where we have been in calculus 1, 2, 3. Okay, so I would call after the limit. So this is pre-limit. That's what we're going to be doing it for a short while. Pre-limit calculus. And the rest is post-limit calculus. We do not choose one over the other and prefer one over the other, because as you can see, these examples I hope have demonstrated that we would like to have both, right? So numerical simulations, very productive, but they're limited in scope in how far you can go with them. Solve problems in a you do only one at a time, one simulation at a time, and literally that's what the computer can do. Only one simulation at a time. You can run 1 million simulation. You cannot possibly be sure that you haven't missed one, which is demonstrate entirely different dynamics, or even maybe it breaks down. Okay, so we cannot assume that it's going to work every time, even though we had very good example when it does. But we also had an example where it does not. So, but right now, so this is the section about discrete forms, is just to figure out, be very precise about what is that we are, what are those sequences are, okay, and how they're linked to each other, because after all, it's calculus, and even though we have it sequences, you saw sequences in calculus too, right? Sequences in calculus. Nonetheless, it is very special, because we're not speaking of limits of these sequences. We speak of the of calculus, which basically differentiation integration. So what is the analogs of differentiation integration? And these are the delta and sigma. Okay, simply differences and simply subtractions. But to be even more specific, it is the positioning of the function and its derivative are different with respect to each other. And so once again, the distinction is where they're defined. The locations are recorded every moment of time. Okay, and then but velocities are either recorded or computed over a whole interval of time. Okay, so therefore there are two different sites, different domains basically of these functions. And so the only thing I want to simplify here is just it's probably easier that if they are equally spaced. Not probably, definitely easier. That's really how we are will be assuming, as we have been assuming that they are all equally spaced, and so the intervals are on the same time, the same distance, and so there is less to work or things to worry about with that. Okay, so then the geometry of this is once again two different loci, if you like, for the two functions. Speaking of the domains, one's for the locations, nodes, for velocities, edges. Okay, so the language that you may have seen elsewhere, nodes and edges. Where have you seen it elsewhere? The terms. Anyone? Graphs? Anyone? Graphs? You've seen graphs? Doesn't matter. This is the simplest graph you can imagine. The nodes are just numbers, and they're connected by edges into a string. Okay, so once again, the perspective is that there will be higher dimensions, and that's why the terminology is not an edge necessarily, but 0 cells and 1 cells, because they are high dimensional cells for high dimensional problems to be solved. Okay, so all right, so then once again, dimension 0. Point is 0 dimensional, and the edge is 1 dimensional. Okay, so that's hence the terminology, and that's also is referred to as the cell decomposition or of interval, which could be finite, could be infinite, doesn't matter. Okay, so once again, this will be h equal, just to keep it simple, And otherwise you can start at any point. And the easiest way is to, if every interval is one, that certainly makes life way easier. Okay, so there's a number, the location associated with each node, moment of time, and there's a number, also a number, the displacement associated with each edge. Okay, so that creates two functions, and naturally it will go from inputs and outputs, even though both of them are numbers. They have different, they're taken from different collection of numbers. For example, over here it could be any, so any real number is possible. However, here it is not the case. Only the either we would. In the case of the nodes, they could be integers, or they could be go half. You know, like with that measuring tape, you go 1 inch at a time. You go half an inch at a time. You have quarter inch at a time. That doesn't matter. They're equally spaced, and the accuracy that we can pick, that's ours. But the point is, on the left, the choices are limited, and so we're not this. That's what we end up with, but rather, with that. Okay, because the domain is discrete. Okay, so they call forms. Okay, so forms, just a letter, forms of two dimensions. Once again, depending on where they define nodes, 0 cells, or edges, 1 cells, and respectively, they correspond to 0 and 1 numbers. 0 and forms give you two numbers. Visual then very simple. As you can see, this if you remember that what functions are, there is, if the domain is specified, each element of the domain produces a number. That's what the 0 form is. The domain is the nodes, and each of them gives you a number. For 1 forms, each edge is in the domain, and then each of them corresponds to a number. So once again, locations, positions, locations, and for each moment of time, as well as velocities for each interval of time. Okay, so that's what we're choosing here, and they naturally why do we care about having it differently? It's sequences. If we just concentrate on this, it looks the same. It's just a sequence, and no more nor less. But why we do it this way? Because once again, the relation between the two of them is very different, and that's the relation between a function and its derivative. Okay, so you may have noticed, and that's related, is in calculus 3. Anybody has taken calculus 3, or is taking? So remember calculus 1 and what the derivative is. It looks exactly the same as the function itself. It is an input number, output number. Did you notice the derivatives in high dimensions do not look like the original function? Can you take an example, for example?
Off the top of my head.
What is the derivative of a function of two variables?
Of 2 variables is.
Anybody? What do you think is the derivative of a function of two variables? I mean, okay, if you now haven't taken calculus 3, unfortunately, then maybe that's not a good question to ask. But once again, it is as you progress the dimensions and the input does not match the output. Okay, so function of two variables means that 2 inputs, 1 output. Then when you do differentiation, it will look very, very different from the original function by nature, not but just the curve is different. A lot of time spent doing that in calculus 1 and 2. But when you go to high dimensions, that's where differences become very pronounced. This is a different kind of difference, but you can see how if we were to compute velocity or displacement in this case from the locations, then as you can see, the reference is into about the interval rather than about the point. Okay, so this is once again, I'm doing it in parallel now without the link, because any combination of numbers on the left and any combination on the right, they can exist. It is the relation exists when we start to do calculus. Okay, so 0 form, as you can see, you can write 0 goes to 2, 1 to 4, 2 to 3. Time always gives you locations, or time intervals give me velocities. That's on the right. So during intervals 0, 1, I was moving 3 miles an hour, and then I was moving half a mile an hour, and so on. Okay, And then, so that's pretty short. You can abbreviate it even further. So you have this, my decomposition into cells, and each cell is marked with a number. So the cells are here, zero cells are the nodes, and each of them has a number. That's where you are, for example. Or if you are concentrating on velocities, then each edge corresponds to a number as well. That's the velocity. Okay, so actually these are functions, and you can write them algebraically, you can visualize them in a very effective ways. You can see here at the top, and then you can write them algebraically. Function, name of the function, parentheses, and equal. The input is inside, output is on the outside. That's what you see in the middle. And then you can visualize it in this manner. The graph. What is the graph of one form and the other form? And one is made of dots, the other one made of edges. Why? Because once again there is no change of the velocity within each of these intervals. So that's what that's our assumption is about how we study motion, which through sequences before we take that limit. The limit that will be quite a bit of work when these or was rather in calculus 1 when these intervals become shorter and shorter, and then poof, and there suddenly you have infinitely many points there. Okay, and this is an example of what is to come. Similarly, two different graphs, very much different graphs, and something you do not see in calculus. Function is derivative, they look the same, but zoom out, and then you have dots there, edges there. It doesn't matter. It doesn't matter. It just looks like the curve. It's literally the first one is made of dots, the other one of edges. But if you zoom out sufficiently, it looks like a curve. Okay, and that's what limit ultimately gives us is the ability to ignore the lengths of those intervals and becomes continuously changing curve. So a curve in the literal sense, not you just have points, separate points that's so close to each other that they merge, but rather it is a literally a continuous curve. Okay, so and now if we were to speak of motion, now we can link these two together through as it is done now. Actually, function is derivative. Then we are right now, if we're not looking at the velocity, we look at the displacement, which means that we're doing subtraction. Okay, so if I was at 5 and then I'm at 7, I have progressed 2 units, and so that is 2. So if I have to have 2 marks, 5 and 7 at the nodes, then I do the subtraction, and the answer is 2, and I write it to associate with that interval. So from 5 to 7, which means that I have progressed 2 units during that time interval. Okay, so that's what is it? It's a difference in the same word difference as in the word differentiation. Okay, so we are doing, as I said, we are reviewing the part of the calculus that precedes that fateful limit, which we just going to review in a minute as well. So as you can see, the formula is a very simple little subtraction. You can put them together in one. Okay, so because the same decomposition. Okay, so that's the node edge, and then each node is associated with a number. So here I have 1, -3, 5, 7, and then I can carry out the delta operation, differences, and I also, in addition, I will assign -4, 8, and 2 to those edges by doing subtraction. So I go from 1 to -3, the progress is -4. -4 from -3 to 5, it's 8 from 5 to 7 is 2. Okay, so that's my motion. I derive the information about location. From it, I derive the information about the. Okay, so that's the difference. It's literally the notation here is a little funky, but you probably this is a better explanation of what I'm looking at. And this is just for the record what the formal definition of the difference of such a function is of what function of a zero form. So the difference of a zero form is computed through consecutive subtractions, and the result is a 1 form. Once again, zero form assigned to the nodes, 1 form assigned to the edges. Okay, so if this is how algebra. So let's take another look. Go back to early calculus 1, and so you have two functions. In case I have functions, I'm looking at two functions with formulas. not like the one the way we did it before when there was data and I did a bunch of numbers and you can just take subtractions. But if you have a formula, you can just do subtraction. That recognize this a little bit probably. So remember the derivative is the limit of the difference quotient, and what we're looking at is the numerator. Okay, so in this particular case, the denominator is actually 1, and so there is not much to look at. But you can simplify. So if your function is 3n squared plus 1, I do the difference, I end up with 6n minus 3. Okay, so and then so anything, if you compare these two, does it ring a bell in any way? Calculus 1. 3n squared plus 1, 6n minus 3. Especially looking at the first two terms, what's the relation?
What derivative?
It is the derivative, right? So not by coincidence. We're talking about the same thing, except we just did not get to the limit yet. But otherwise, they're already there. So, and that's in the next line here is, this is definitely a familiar computation from early calculus 1, computation of the derivative. And so the numerator is so there's a formula for the function. Now h is present, so I'm computing the difference quotient in this first half of the computation, and that's the definition divided by h. That's the run, and then I do not really need it if I do the simulation. We never did this, right? Why not? Because I want a simulation. I have a bunch of points there. I can plot it. It doesn't matter how complicated the formula is. The computer will compute it for you. So that if I have this, I just go straight to simulation. So that simplification that follows right here is only because I'm going to take the limit at the end. Okay, so these are the two routes that you take. So either you want to actually have a continuous calculus here, or if you just want a simulation, numerical simulation of the phenomenon, then you don't have to simplify. If you simplify, though, then you can see things have to be that. I hope you remember some of that. So you have to you need to get rid of the denominator, because remember, why do we get rid of the denominator?
Limit as isn't it like limit as h goes to 0?
That's right. So you don't want to divide by 0. So unfortunately, every single time it works out. Okay, so every time you simplify, move stuff around, h cancels out. Okay, and so this is the difference quotient. I have found a formula, which we don't need again, for the difference quotient as a function of h simplified. Okay, but then now we're taking the limit. What's going to happen? H goes to 0. Now there is no division by 0, and so everything is fine. And I end up with what I end up with. X squared, because the other two terms disappear, become 0. Okay, so also as you can see, this is the trade-off. On one hand, we are the algebra for right, what's on the surface is that the things have simplified, right? So if we try to do discrete calculus, we end up with this. If we try to do discrete calculus by hand, we end up with this complicated formula, or h equal to 0. Okay, h equal to 0, and the terms with h disappear, and you have formula simpler. And that's the great simplification of calculus that we achieve. It's not, without the price to pay though, because remember the function that is continuous. It's not a sequence. It is not just to be plotted by the computer. It's a formula, and then you have to do something with it, and whether or not you're going to do it is unclear. It's actually suggests what you follow with that from here is continue doing it by hand. So it's perfectly suitable for Newton's times when everything was done by hand pretty much. So that's great simplification. It makes simple it for the person, but not necessarily for the computer. So if you were to continue with algebra by hand, then that step is crucial. Things would have simplified significantly. And this question is kind of related to, for example, just a free fall. Remember free fall formulas, and you end up with, and remember what that kinematic equation is, or equations from high school, probably. A falling object. Anybody? Recollection of what anything about how the elevation of an object that is falling down depends on time. Right, it is quadratic, right? So there's some coefficients there, but it is quadratic, depends quadratic. And that's why does it work out, why you can actually show it to high school students without doing any calculus, because the problem can be solved. It's the algebra, once you end up with something quadratic, well, so you need a quadratic equation maybe, and then you have everything, everything from it. Anything more complicated, and the formulas also might be so complicated that, that even such simplification will not solve any problem for you. So you actually need Newton to describe not a free fall of an object, but rather an orbital motion of, say, moon around the Earth. Okay, so that's to derive it from his law of gravity. Okay, so that is a problem of this course, by the way, is how hard it is to end up with a clean formula for the one planet orbiting another. Okay, so it takes way more than that, and so we were lucky because there's never a guarantee that it actually can work out. Anyway, okay, so that's just once again a reminder. H, this is delta T, H now is the parameter of the model, not anymore. Simplification is once again for people, not for not computers, I'd say. And then you can do it with any other function. And so we proceed on to the post limit calculus. Okay, so simplify the algebra velocity. Okay, so okay, I'm sorry. In the reverse, I have to discuss the flip side of calculus. So once again, remember the 2 points, the delta and sigma. Just as the 2 points, the derivative on one side, and there is a integral on the other side. So in the discrete environment, we're dealing with summation. So what's the inverse of fraction? It's addition. Okay, so if we were subtracting, doing those differences, now we are doing addition, and that's what on the first diagram plus what we did in reverse. So instead of knowing location, find distances. We know distances, displacements, and find the location. As you can see here, so the green one is given. So we know how much we progressed every one of those during those 1 hour intervals. And then what you do is also in addition, if you know also in addition your initial location, then you can on top of that you start adding things up. So 1 plus -4 gives you -3, your next location. Then you add 8, which you're at 5. Add 2, you're at 7. But that's what sigma stands for. Okay, so sigma is the sum of a sequence, or rather sum of a one form. So one form of those numbers corresponding to edges is given, and you can find a 0 form from it by doing summation. So that's what this is. So once again, the formal definition. That's I hope everybody remembers sigma notation. Everybody from calculus 1 and 2. Remember, you actually did series in calculus 2, so that's we might do them later. Okay, so just to remind you that this is the construction of the Riemann sum. So if the intervals are not unit intervals, then you to reconstruct our locations from sequence of locations from the velocities. That's what you need to do in this computation. Okay, so you have to multiply over here the velocity times the interval of time, length of the interval of time, and that gives me the displacement, and then you add those displacements one at a time. Okay, so each of those bars over there represents the once again, width is the time interval and height is the velocity. And when you multiply them, on one hand you have displacement, time times space, or if you think in terms of geometry, it's the area, right? So remember that's the Riemann sum is the area. Riemann integral is the sum under the area. That's what you see. And the Riemann sum over there approximates the Riemann integral on the left. Okay, so that's once again calculus, the end of calculus 1. Sounds familiar? So, okay, so that's the formula notation, and then naturally there's that fundamental relation between the difference. It sounds very predictable. It's the same as the relation between the derivatives and integrals, except to be clear, this comes first, and then from it, what we say the fundamental theorem of calculus is derived from. Okay, so look at it. So if I start, this is written right here. So if I start with 0 form in red and then compute the 1 form by taking deltas, okay, what if I take those deltas now and then not deltas, but rather 1 form in green and start doing summation? Where do I end up? I end up where I start. You see what I'm talking about here? Start with red, do the differences, as we already did, produce the green numbers, those 3 numbers. Okay, so then take a pause and then forget about the red numbers for a moment, and then start doing addition. Well, you can forget about all of them because you need to know where to start. But if you already know that you're supposed to start with 1, you will reconstruct -3. How? By adding -4 to -3. Okay, and then -3, 8, and so on. You will get the red numbers at the top. So that's literally deltas and sigmas work in the opposite directions, and as if they are, what's the proper language is inverses. Sure. So they, when applied consecutively, they cancel each other out. Okay, so that's the fundamental relation, and either you delta then sigma or doing sigma then delta. The result is almost the same, except one little thing, and that is plus C business. C business, because if I start with instead of 1, I start with 0. Okay, alternative, I start with 0. I end up with a -4 plus 8. 4 plus 2 is 6. Okay, and then you ask yourself, what's the relation between these two? What's the relation between these two?
Just missing 1.
And plus 1. Right, so plus 1, so plus 1, that would be plus 2, plus 3. That's what that little kind of ritualistic thing, plus C, when every time we integrate, we have plus C. That's what it's about. Infinitely many possible answers. When you have 1, you have all. So that's the good news. You only have to do it once. And typically you can start with probably adding from 0 rather than from 1. And then just remember that that sequence that you have, you can just add it, and then that it will be shipped up and down, producing more and more infinitely many answers to that sequence. Sigma is dependent on your initial value. So algebraically speaking, that's what we're talking about. Once again, 2 sides of the algebra fundamental theorem of discrete calculus. Delta followed by sigma, or sigma followed by delta, it produces the same result as if nothing has happened. Assembling, you have a bunch of blocks, you can assemble from them the staircase, or you take them then apart and you coming back to the same place. The only difference is then when we take the limit, then it becomes way more complicated. So that's the price we'll pay for having what amounts to infinite accuracy, right? So you can think about these things as if they approximate some continuous motion. After all, we are moving through space. The time is continuous, the space is continuous probably, and we approximate these processes with in a discrete fashion like this. So it's an approximation, and then so it's a bad, but so let's avoid approximation. We take the limit, and then the price you pay, instead of this little summation, you replace it, or a little subtraction, you replace it with different derivatives and integrals. Okay, so they're not simple. They're not simple to compute, and not as simple as this, and they're not simple to understand necessarily. So it's all a challenge. But well, we pay that price because it works. It just works. But if we do not pay that price just yet, so this is how you can execute the 2 in reverse, just with spreadsheet. Very easy to to program these 2 operations because they're so elementary. Look at it, you can do it with Excel, no trouble over there. Addition for the sigma, subtraction for the delta. You carry out them consecutively, and as you can see, the beginning and the end is the same. Delta followed by sigma, the result is the same. Not the same. The beginning is the same at the end. Okay, or you do delta sigma then delta, and then once again you have your answer. Your beginning is the same as the end. So now this is post-limit, and this is where once again we have to pay the price. Okay, so and here it is. It is something that you've seen before. Remember, we've been talking about discrete forms. There are also forms in the post-limit in the familiar infinitesimal continuous calculus. but they look something like this. So the question is here, is dy dx a fraction? And the answer should be, you should be, have been taught that the answer should be no. And now I'll try to turn that around and see in what sense the answer could be yes. Okay, so to be fair, both Newton and Leibniz thought of this as it was a fraction. Okay, but they were thinking in terms of infinitesimals, and what that means is they will criticize, especially Newton, by philosophers primarily. And so what is the infinitesimals thing? How can something be infinitely small? Isn't that zero? Okay, so that's what you can say if you want to use that language. Fortunately for all of us, the problems with this kind of approach, more philosophical than anything else, was fixed in the 19th century, and so that's how we get that we have epsilon delta, we have the limits, and all that had been worked out. So we're not going to throw it out, so that's still kept. But so in what sense dy dx can be understood as a fraction, and how could it not? Well, let's figure out if it does make sense. What would the dy dx be? So dy dx, a fraction. So to be a fraction, it's the only way to understand it is that the actually dy and dx both are numbers. Well, certainly it is literally the numbers. So remember what we just did before, delta y over delta x, those who are numbers, surely. And then you have y sequence, and you did delta, and then you say with x's, and these are two numbers. So similarly, these are two numbers, but where do they come from? So dy is one number, dx is another number. Then these are the names of these variables, which are not the same, not y and x. Okay, so they come from somewhere. Okay. So just what remains is to figure out where they come from. But in such a way that when we do form that fraction, that should still be the derivative. Where from? So we're still assuming that dy dx is say y prime. It is the derivative. Okay, so it's just different notation. That's the notation. The Lagrange notation y prime is obscure. It is very compact, but it hides for us the fact that it comes from the fraction, that fraction over there, and also that dy dx could be a fraction, and it is in a certain sense. So okay, that's the limit, and this we just say it's notation, but we can figure out what it is. It's the slope. Okay, so delta y over delta x is definitely the slope, and we have, remember, we had 2 points, right? And then we draw a line. Okay, and then this is run, and this is rise. Okay, so then certainly we know that that's for the difference quotient. The rise of the run, the slope of that line, but technically the curve, our curve might go like this. So then what we do know is that the derivative is the slope of what? Oh, the tangent line, right? So this would be called the secant line, and then it's very naturally what it is. There are 2 points, and it determines the line, and then we propagate this line, 2 points, okay, line, and then its slope. Makes perfect sense. With the derivative, it's not working at all because it's kind of a circular, because there's only 1 point. There is no line. Okay. If there's no, so how do you plot? How do you plot a line when there is only 1 point? What else is missing? You give it a slope. Then you can either build a line from 2 points, or you build it from a point in the slope. But we don't know what the slope is because the slope is the derivative. So unless we already know the derivative, we cannot plot the tangent line. So it's all circular. Nonetheless, it is a fraction. Okay, so if that line is constructed, the tangent line, then just look at it and then say this is a rise, this is a run, and just call them. Then the run will be dx, and the rise will be dy. Okay, so here's an example. If this function dx squared is equal to 2x, and let's pick point 0, 0, okay, So, the dy dx is 2. The derivative is 2. Okay, so once again, that's the computational calculus 1 is this. And now what if dy dx is a fraction, then we can just, to demonstrate that we treat it as a function, we write y is equal to 2 dx. Okay, so if we accept that dy is a number and dx is a number, some kind of variables, then this is how they're related to each other. Okay, so it is, there's nothing special about it there. That the only problem is it's uncomfortable after so many years of doing mathematics is having names of variables with 2 letters. It is literally, these are literally the names. Names, dx and dy. Where they come from, that we know where they come from, but they come from delta, they come from difference, that's what d stands for. But nonetheless, it's just the name of the variables are dx and dy. And they depend on each other in this manner. So dy, that variable, is expressed in terms of dx as by simple multiplication of 2, which means I can actually plot it here. Yeah, plot it right here. Okay. It has slope of 2. So in addition to having x's, x and y, we have also axis dx and dy. Through that point, this is our point, okay? And through that point, the graph passes, but we actually ignore the graph of the function, the blue one, and we concentrate on the red one, which is the graph of the tangent line, and it is simply expressed in terms of these dx dy, the difference of x, the difference of y, and the natural dy is equal to twice dx. Okay, so there is nothing really now so repulsive to mathematics here is to think of dy dx as a fraction if you know where they come from. It is challenging a little bit to actually having extra structure to worry about on our plane because every point will have this system. Okay, so this is just one point on the graph, and when we pick a point on the graph, then its slope is determined, and therefore the derivative will be then interpreted as the slope of that line. Okay, and then, but on the other hand, it's just like with every equation, this is I don't know, u is equal to 2v or y is equal to 2x. Well, it's all the same. It's all the same, and then we just happens to have weirdly named variables. That's all. And it is, you do appreciate the simplification naturally. Well, that's what the tangent line is for, and it is a linearization. Remember linearization, so replacing the curve with a straight line. And especially, so it simplifies computations, as you might remember from calculus as well. So if you have multiple points, as I said, you have to carry out this operation every single time. And so here I have the graph of the function is y equal x squared plus 1. Here I pick 4 points, and then in each of them, these points, in the vicinity of each point, we have to build the same. Okay, so it's not like the same dy and dx because the slope is different in each of these points. Okay, so that's the one graph of the same function, and then I have 4 points on the graph. Okay, so these are the points 1, 2, 3, and 4 have different tangent line, and therefore, when I was to build that dx dy axes, which are these dx dy right here. So this is x, this is dx, this is y, this is dy, and then with respect to this new coordinate system, I draw the tangent line is expressed in terms of this new system, and therefore what we end up with is a very simple linear equation with the slope being the derivative. Okay, so if derivative in the first point over here seems to be what is a -2, so the equation of this line right here is dy, this is dy, once again dx dy, right? And so the equation is dy is equal to -2 dx. Okay, over here, once again, I zoomed in, and I dropped, and I forgot about the rest of the graph. I zoomed in on that particular point, and but forgot about everything else. And as you can see, the tangent line is horizontal. Dy is equal to 0. Okay, so there is no change in the vertical direction. So dy is equal to 0. And then third one is right here. Okay, the slope is equal to 2. You see the slope is equal to 2. Over here, the slope is equal to 4. And that's so the derivative is indeed appears as the slope of these straight lines. So the challenge, of course, is one point at a time. So, but that's what the derivative is. It's different at given point, and therefore the graph is different, and therefore for each of these locations there will be this equation. Bad news, but we can just do this. Okay, so this is now you have a mixture of different variables. We have x is present, and we have the x is present, dy present. So it's like three variables to worry about. But this is nothing but, to be clear, this is nothing but multiplication. So if you want to know what the slope of that line is at every point, what the graph, or rather, what is the formula? This is the formula of the tangent with respect to dx dy at each point xy. Okay, so as you're moving through the point xy, their slope is different, but every line has an equation. Every tangent line has an equation, and you have four of them right here given. But you don't really need all of them to treat it separately if you have a formula. So that's what it is. And where does it come from? Of course, dy dx is equal to 2. That's really, if we treat dy dx equal to 2, we can jump straight to this from a fraction, and we jump straight to this equation, and that's called a differential form. Okay, so not a discrete form, a differential form, and so its challenge is that there are three variables present at the same time. Naturally, that the right-hand side you've seen before. The right-hand side looks familiar, this part. Looks familiar? Where did you see? So the naturally what's on the left is familiar, but on the right too, especially what I highlighted. Where did you see 2x dx? Direction, anyone? Right, so it's just integral is missing. That's all, but it is a direction. So that's the only occasion when you see it. And so it turns out that's the another way to look at the integration. It is we are integrating differential forms. Okay, so that's a differential form to be integrated, and the answer is we know is going to be 2x. Yeah, like this. So dy is equal to 2x, and then dy is equal to 2x, and if you integrate 2x dx, you end up with x squared over x squared plus c. Right, so that's the integration. Okay, so it fits. It just an extra wrinkle added to calculus, and then differentiation looks we added extra idea here that dy dx is a fraction, and if all you did have to do is you just multiply by dx to produce the formula on the right. That produces what we call a differential form, and that differential form can be integrated as I just did in the same manner as before. Okay, so that part doesn't change. So no formulas to be added. Which is the interpretation of the integral will be slightly different. Well, not different. It's the same. It's an additional interpretation. You can still think about that formula over there. You integrate. You would say I'm integrating to x, right? That's how we would would speak of the integral on the left. But now we can also say that, well, actually, we're integrating the differential form, which includes the x. And the advantage is it's less magic. Okay, so because you realize that it's not, you have integral on the left, dx on the right. Half of the students forget dx. They just write integral to x, because what's dx is just kind of a stand there doing nothing. But now you know what dx is. It's multiplication there. So what's the symbol between 2x and dx? It's just multiplication. And 2x is the function with respect to x, and then multiplied by that extra variable dx, and you know what the meaning of that dx is too. So it all fits. So that's what we're talking about. So dy dx is once again from the equation. If you start with using the combination of the two different notations. with the derivative, and then you treat dy dx as a fraction, multiply, and then what you end up with by multiplying, so it's a division on the left, we have multiplication on the right, and then you end up with what we call a differential form. Okay. And then now so there's a function, and then there's its differential form, and then there's a differential form. So it is the relation the same as what we just talked about, that is the different animals for functions and their derivatives. Okay, so if you need a picture, this is another picture here to illustrate what we're talking about here. There's a point on the left, there's original interpretation, the graph, the point on it, and then you can draw a tangent line over there. But the interpretation that we are pursuing now is we erase everything. We erase this part, okay, and just concentrating on that point, which is how derivatives treated anyway. Tangent line, you have one tangent line at a time, and then we rewrite our equation, this one, and we rewrite it right here as the relation between the two variables. dy is that vertical variable, dx is the other horizontal variable. The relation between them is linear because this is nothing but multiplication over there. So it's a linear function. dy depends linearly on dx, and then f prime is simply the slope, one single number, and you can plot it. Okay, so that's the meaning behind it. Okay. So any questions about this? That's the meaning of it. They're called differentials also. You may have heard this. It is usually mentioned in a calculus course as such. So there's a word to describe these two variables. Once again, differentials of x and y respectively. So that's the transition. This is the another way to look at differentiation. So x depends on y depends on x. And here, look at it, what happens after differentiation has been carried out. dy depends on x and dx. Okay. So that's the complexity that we introduced, is that there are two variables to worry about on the right. Okay, so linearization, I'll let you. I'll probably let's quickly run over, because linearization is such an important topic in calculus. And after calculus 1 and 2, you surely should be pretty well familiar with that idea, and it comes up throughout differential equations. So linear approximations, everybody. What's a linear approximation of a function at a point? There's a curve, there's a point, and then we approximate that point in the vicinity, that curve in the vicinity of that point. What's the meaning, geometric meaning of that? Picture might help, especially in the middle. What's, how do you understand the word approximation? What does it mean to approximate anything? Wait.
Take your best guess.
Well, yeah, outside of mathematics, I guess it's acceptable, but for example, how do you approximate pi? You can guess if you say 3, that might be okay with certain circumstances, but not in general. Then you the point is that you can improve and improve and improve. It's a scheme that will produce better and better approximations. And if you need to approximate 1/3 with decimals, you go 0.3, 0.33, 0.333. So it's a scheme, and at the end, the absolute approximation that of infinitely many threes, that's the actual value of 1/3. Okay, so the scheme that will, and that's why we need calculus, so that the limit of this scheme of approximations actually gives you very little number. Otherwise, your approximation is no good, because approximation is only good if you can achieve any approximation of any accuracy that you want. Okay, so that's why we do it the way we do. And then how do you achieve that when we not speaking of one value, but rather one number, but rather we speak of a function? And the answer is here, approximation of the curve is what? Oh, what is the point? The point of approximation is simplification. So you replace pi with 3 or 3.1. Why is it simpler? Because pi has infinitely many decimals. We cannot possibly know all of them. So it's simplification. Similarly, if we were to approximate a curve, what is the simplest way to approximate it? What is the simplest object that you use to approximate? The tangent line, the straight line. That's the answer, actually. The answer is if you would generically, what do you pick? A simple object to approximate a curve. Well, let's not make it curved anymore and make a straight line. Okay, what line? And that you go through in calculus 1 to explain that the answer is straight is the tangent line. So that's the exact approximation of the tangent line of the curve, but it is ultimately the answer, the absolutely accurate approximation. Out of the class of lines, you pick one which is the best, and that's the tangent line. Okay, so any of that rings a bell? I hope. No? Well, here's a more trick question. Why is it? What does T stand for? What? No. Instead of thinking calculus 1, think calculus 2. What? Yeah, put here, what if I put subscript here 1? Actually, that should probably. So it does not stand for tangent, but it could, obviously. So usually put all L there to emphasize this linear rather than T tangent. So the linear approximation.
A Taylor approximation?
What Taylor approximation, right? So this is first order Taylor approximation. And so T stands for Taylor. T2 is a quadratic approximation, and on and on. So that's the point of it. But here it is a linearization, replacing a function with a straight line. That's a linearization, a particular kind of simplification. You can replace it with, for example, a parabola. That's another better approximation. Okay, so right, and so that once you have a tangent line, you have a point, you have tangent line. So you totally replace. Then you throw out the your function. There is no function that replaces with this little function. So this function is x squared. At 1 produces 1 plus 2x minus 1, x minus 1 over here 1, and that's the equation of the tangent line. And it is best. It touches. Remember, touches one of the only one linear line that touches the graph is the tangent line. So that's the justification for. If you zoom in, they will be indistinguishable. That's the reason why we choose it. Okay, so the bunch of tangent line. Unfortunately, that's the trouble with this. You have to do it one at a time, but then we have all of them at once, and that's what we have. Okay, so once again, back to integration. This is the difference. This is the difference calculus 1 and on calc 1. And this is beyond that, and say differential equations more general, and that is a replacement of what is that we concentrate on, and the answer is differential form. So it is kx dx. Okay, function multiplied by dx. So it has two variables there, and it actually, once again, you don't have to forget about just like with the derivative. That's where integral comes from. It comes from the derivative sum. And that's where you have literal multiplication. Okay, so then just like with derivatives, delta becomes d's, but otherwise, and then you might forget, but there's a division there for derivatives. For integrals, you might forget that there is a multiplication there, but there is. And so that's why the language of differential forms actually speaks more better about where things come from, because they come from very simple algebraic operations, subtraction subtraction combined with division, or addition combined with multiplication. So it's all still, it will be intact, it's still intact in our notation, because there's a gap between kx and dx, but that means simply that there's multiplication. So that's, and then there are two degrees, just like with discrete forms, there are two different differential forms. So except we only care about two of them, just like in discrete case, one form is if it has dx. Zero form, it does not have dx. Okay, so so that's the differential form of degree one, some a function of x multiplied by dx, and that's what is being integrated. Okay. Yeah, so it's literally a function of two variables, because if you haven't seen functions of two variables, then that might not help, but it is surely helpful if you do what you do. So remember the chain rule. Okay, that's once again treating dy dx as a fraction is not only profound, it is very convenient, right? You just cancel, you write dy dx, and then you write dy du, du dx, and dy you can cancel, justifiably cancel. If it is a fraction, then you're not just playing games here, you're literally dividing by du, I'm sorry. So once again, you have a composition from x to u to y, and there are therefore two derivatives, dy du, and du dx. And then if you multiply them, there will be cancellation of the numerator of the first and denominator of the second, and gives you dy dx. Okay, so this is the chain rule. Very well, once you see it, you will remember that the chain rule is very natural. If you write it without these, it is very complicated. It's easy to make a mistake. But here, it is very much explicit. So don't forget that. Don't forget also this. If we have dy dx, what's the meaning of dx dy?
That is the interval, the derivative of x with respect to y.
Right, that's right. So in other words, the word is the inverse, right? So you have y depends on x, that's your function, and then, but then if there's an inverse, x depends on y, and then what's its derivative? All you have to do is to flip it. If it's a fraction, you are okay flipping it. Okay, so another reason why we do it this way, the way we do it. Okay, so integration by substitution, we're gonna do that a little bit. Remember this? So if you've done in calculus 2 any amount of integration by substitution, you've done this. Okay, so here you have, as you can see, we have a new variable, and when we substitute, we have our integral being, this is the yeah, so you have I don't have it here, integral f is this fx. Second, how do I want to put it? It's not fx. It is integral f. It looks more complicated than the zeros, but you probably seen it before. Okay, so if it happens to encounter integral like this, how do you solve it? You introduce a substitution, you go g of x, then this is du dx. Okay, and then if you plug it into, if you carry out the substitution, then there will be cancellation of dx, which is only legal if dx is a number, and if it is a number, we cancel it. So that explains that trick that you do in calculus 1 or 2 when you do integration by substitution. Meaning, well, what does it mean? It means changing variables. So if you integral with respect to x, this is 1 over x, and then it becomes integral over u. How you carry out the substitution, but it's very easy. You must have made that mistake when you did integration. You forgot dx, and you just replaced dx with du, but they're obviously not equal to each other, and therefore that was a mistake. Okay, but that's clearly two things, two different variables, different names. They're not equal to each other. So the benefit of this approach is that you're not going to make a mistake like that. It is a literal substitution, but because there are two variables, okay, so if you look at it, there are two variables. There is a variable that is u, there's a variable that is x, but there's also a separate variable that is dx. and they are to be taken care of separately. So x is, you know what x is, it's expressed in terms of u, but dx is also expressed in terms of u and du. Okay, that's what happens over there. Okay, and so there's a cancellation, and then you have a neatly transition from a formula that is with respect to x to the one with respect to u. Hopefully, it simplifies things, and then you have your you can finish the job. So this is really the formula of differential by substitution. You if once again is u is equal to g of x. Okay, so this is the what I've just been talking about. What du is. Whether it's integration by substitution or not, this is really what the algebra differential force is. You have a function, and then what do? You do this kind of fancy differentiation. Okay, you write du is equal to g prime dx, which is the same as du dx is equal to g prime. So it's not really that far-fetched, but it is what allows us to carry out the integration, to turn integral into not integration by substitution, which is misleading term, but rather change of variables in the integral. Okay, so change of variables from x to u. How to do it? That's how. Okay, so that will come out as well. Something. So differential form of degree 0 is simply any function. A differential form of degree 1 is the one with dx, and you go from one to the other by doing what we call exterior differentiation, and that's the formula. So you don't have to remember the formula. Just remember that there is this substantial theory that support this different point. About that, just to remind you, because we're going to progress from this into more complex situations, and so let's carry out integration by substitutions. It's just a review of calculus. Okay, so I have my function right here, x sine x squared dx, simple one. You can guess every time you see compositions, especially you can tell compositions when you see parentheses. Okay, so then whatever is inside the parentheses is your new function, or rather it is your new variable. Okay, so I want to convert it, hopefully with simplification, into integral with respect to something else. Okay, so how do I take that x squared and hide it? And the answer is call it a new variable. So u is equal to x squared would be a natural choice for a new variable. Okay, and then so that would be, so if we start thinking about substitution, then naturally u will simply go over here, right? No problem. X squared would replace with u. Over there, what else goes over here? We replace x squared with u. What do we replace x with?
U.
No. U is replaced with x squared is replaced with u. X is replaced with square root of u, right? Square root of u. And then the last question is, once again, doing it very carefully one at a time, dx is replaced with what? What? Well, exactly no. Exactly the point I tried to make. These are two different numbers, and they cannot possibly be equal to each other. And the transition is taken care of by that differentiation I just put forward like this. So this is a y, but you can have a u. So let's work it out. Let's work it out. This is it. Okay. Du is 2x dx because u is equal to x squared. If I start differentiating that expression over here, what I end up with is this. Du is 2x dx. So once again, it's a different way of writing du dx is equal to 2x. It's still differentiation, but it's written rather than a fraction. It's written like multiplication. 2x times dx. And then now from this you know what dx is. So that's the point. We need to express two different variables. What d is, it's differential. It's a change of the variable. Naturally, the two different variables, they do not have different changes, but the changes are related to each other. So that's what we are looking at here. That's how they relate to each other. And then dx is equal to du over dx. And so I don't really need this anymore because there will be cancellation. I replace dx with du over 2x, not dx, not du. And then that's what happens. So as you can see here, once again, x squared is replaced with, I think I skipped over too quickly, but I have an integral square root of x, square root of u, sine u, and dx is this du over 2x. Yeah, I don't need this. It's actually easy if I just cancel it out like this. Okay, so I actually keep x, so that it would be easy to cancel it, sine u. Okay, that's what used to be sine x squared, and then dx had been computed d over 2x, and then I cancel it out, and that's what I end up with over here, 1/2 sine u du. It is a simple integral, it's easy to finish, but we're not gonna do it because the point is a change of variables. So let's see, change of variables is what we are after. It is so common in mathematics that yeah, cannot be overstated. It's like switching from pounds to kilograms doing physics, for example, and that's everything supposed to work out. Every single formula that you used to be doing with pounds, now you do it with kilograms, and everything it should be perfectly. It's just you turn a crank, and everything is perfectly works out in the same way. So that's what those substitutions are. And so, well, and now that's so to how to convert calculus from one unit to another, and there are a bunch of them. So that's how. Okay. So that's we just talked about this. You can integrate any one form in the literal sense. It's just a matter of notation, no more than that. Because once we write that integral, it is not. It's not new. So this is old. So we have a differential forms g function of x multiplied by dx. We form an integral like this, and then we just integrate it as if nothing has happened. Okay, so that's the thing about it. And then that's what the fundamental theory of calculus looks like, pretty much the same, except as you can see that dx is hidden. What's differential forms? That's one, and okay. So all right, so I guess I'll stop here. So dismissed. You can ask questions. I'm still here.